Okay, everybody. So now we're going to start talking here about uranium. Um, Uranium was discovered in the 1700s by a German scientist. Um, we don't need to go into like the full chemistry of it, but one thing I really want to note is that uranium is and everywhere, everywhere. There are trace amounts everywhere. Have you guys heard of radon gas poisoning in your basements? That's what that is. Uranium is everywhere. So why is it such a rare mineral then? Well, it's not that it's a rare mineral, it's that in economically viable deposits of it, that's very rare. And that's where it works quite well of it in here. So I really wanted so we know this spits out radiation, which is available everywhere and everything. So all these videos here I will include down below. So you don't need to know this, but really common, right? 500 times more common than gold. It is in the Athabasca Basin here. So it is all located in the Athabasca Basin. Why here? Well, this is because it's just where um it's physical contact. It's physically touching something called the Precambrian basement. Basically, well, I don't know, we'll talk about that, but I really want to make a note here is why are all the mines on the edge? Where are the mines here? Well, there's uranium there. Absolutely. There's good deposits of uranium there, but I want you to think about this like a bowl. So, there's uranium all along this edge. Where is it closest to the surface? Around the edges here, right? So you dig in this spot because this is closer and it's cheaper, and that means it's more economically viable. So the stuff in the center here, it's there, but you got to go way down. We're looking at this stuff here then. The other thing I really want to make a note is that deposits are only 50 meters times 50 meters times 25 meters. Think about a football arena, a football field. It's half the size of that. It's not that big. They're not that big. So same thing, this video will be available for you. Why is it important? Generally speaking, we use it for fuel and a couple other things. So it's used in nuclear fuel bundles, right? So it's used to split atoms. It boils water, that makes steam, that turns a turbine, that makes electricity. Yada yada. You guys know how electricity is made by now. Um, but one thing I really want to make a note here: 10 grams of uranium. Now that is half the size of a flash drive. So half of the size of a flash drive, 10 grams. I literally have not a real sample, but a fake sample, but I have it tucked away right now, so I can't really show you. Maybe I have yes, yeah, okay, here. So something that's about this size, not that big, maybe a third of the size of this thing. So a third of the size of this. That's 10 grams of uranium. That has the same energy as 4 barrels of oil, or 20,000 cubic feet of natural gas, or 2,500 pounds of coal. So it's very energy dense. So it's very energy dense, and this means it's one of the cleanest sources of energy. Now, obviously, there are always the accidents of nuclear stuff, or in the nuclear regions and radiation. That's the major concern, right? But luckily, it's not the 60s and 70s anymore. We've advanced safety and technology quite substantially. Now, Saskatchewan is the second largest producer of uranium, and I believe we're the number one reserve of uranium. So Sask Power, we've at this point we've heard about small nuclear reactors, so SMRs. So they're planning to have these out in Saskatchewan by mid 2030s. So these can power, a couple tens of thousands worth of houses. We also are the only place in the world, only place in the world to have microreactors. And I will show you a picture of that a little bit later here. But a microreactor is just a smaller reactor, right? So look at this. So here's your large regular reactor, right? Oh, look, it's the Simpsons one. So this can do 700 megawatts. A SMR can do 300, and a microreactor can do 20. So why are we designing these things? Again, we're the only place in the world. Well, you can attach these to direct businesses. For example, Regina is getting an AI data center. You can attach one of these directly to that to fuel it, to energize it. We could send one of those up north, for example, to power a small town there. So these are things that we can do. It's very good for off-grid or edge of grid living. Think about this. If you are in northern Saskatchewan, the real north, you don't really have power. You survive off wood burning fuel. What if you have a massive snowstorm, right? So that's where these really come into play. So this here is a micro reactor. Literally, this is the size of it. Here's one person, here's a second. It's 2.5 people tall. Not that big. This is an SMR. I'm not going to go into what this looks like, but just be aware of it. Or sorry, how this works, but just know about that. So why is uranium important? Well, it's responsible for 8,000 jobs, and most of these are for indigenous people because most of the uranium is up north and they work with their local constituents, which is what we'll talk about here. So it's responsible for 8,000 jobs, and this is going up because we are mining more and more. We have new mines coming up. So this is projected to increase a lot. There's an annual salary of $115,000 on average. They sell $1.6 billion of uranium a year, and we produce 20% of the world's supplies. It has other uses, of course, beyond just energy. It's used in biomedical imaging. Hey, look, here's an X-ray. Use it to preserve foods. It's in smoke detectors and a couple of other things. So again, you'll give this video a watch. Um, So again, it's the sedimentary that's left here. So again, we know that there are trace amounts everywhere. So how do I get a big deposit of uranium? How do I get one of those? Well, I take a bunch of the little bit of it everywhere and I make sure it all goes to one central place. So sediments through water brought it to a central point. Over time, millions of years, it all collected, and now I have a giant amount of it. Generally speaking, it's because of water. So I really want to make that point here. Water. These are, what these look like. Now, the in production ones are ones that are currently happening. The red ones are ones that, we'll do later. And the past producers are ones that we've already mined. So I went to Cigar Lake and McArthur River earlier this summer, for example. I got to see their mines. So it's not that deep, right? It's about 500 meters here, right? For these ones. Some of them can go deeper, but generally speaking, why is this one so deep? Why is this one so deep and narrow? Again, water flowed it to a central point. So it's drip, 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 and it's slowly eroded over time and collected. So again, you can see it's on this Athabasca sandstone basin. That's why there's the bull. There's the bull. So that's why we mine it at the edge. So I went to Cigar Lake. You had to fly in. Yay, private jet. Cool. So, I don't need to worry about that. You don't have to write all this down. I'll tell you from at this point onwards, I'll tell you what you have to write down. Generally speaking, here you go. You do need to write this down. So pause the video, write that down. So again, where we get these deposits is it's slowly collected into a single spot over millions of years through water. So it brought the trace amounts everywhere into one central point. How do we find it? You don't have to write this down, but we use air, we use ground surveys, lab analysis, and core drilling, which I'll talk about a little bit later. Don't need to worry about that. So the core logging here, This, for 1 meter of core logging, that costs $6,000. So it's very expensive to sample this stuff. So you and me, the government does not own this. They don't really get a lot of money in the they get some, but they don't get as much as like potash or something because it's very expensive and it's kind of a gamble whether you're going to find something. So we use these airplane surveys, these gravity surveys first. Then we send people on the ground, then we collect samples before we move to core logging. We only core log when we start to become a little more confident that something's there. Once we discover that ore, then we determine if it can be mined, right? Because it needs to be profitable. So we look at how much is it? How deep is it? What's the quality of it? And so on and so forth. So, right, you'll want to write all of this down, all of this. So 3, 2, 1. Now, one thing I really want to make a note here is that to get a mine, you need an environmental assessment process. Now, this has 9 steps. You will want to write these 9 steps down, which you can see in this wheel here. So pause the video, write that down. So an environmental assessment examines how this mining operation will affect the local people and the local environment. So how is this negatively going to affect the people here? How can we mitigate or prevent these impacts or limit them? And you need to have proper scientific evidence. You need to be working with the local people there. And those are the foundations of this. So the first thing we do is we need to do a proposal that, hey, I want to mine here. And so government, here's my proposal. Let me mine there and I will pay you this much. Cool. So I do that. I do my application. They screen me. They're going to look at the area. They're going to look at me. And then we do an impact assessment, which is looking at, how is this going to affect this? How are we going to mitigate this? It gets reviewed. Then it goes to the public where they comment on it. Then the government decides on it. And if they approve it, you get your license in and you start digging. So you need to do this before you take the first shovelful of dirt. So this must be conducted, you want to write all this down, must be conducted before construction happens. So this looks at all the ways it's going to happen. Remember, the present condition of the land, the water, the air, and the local plants, animals, and land users are all considered, conducted, and recorded. So we look at all stages, the construction of the mine, the operation of the mine, and the decommissioning of the mine. And we look at any impacts or risks as well, such as, are we in an earthquake prone region? Is there a chance that this mine might not be profitable, or could it flood, or could it leach into the groundwater? So there must be mitigation plans for any risks. So it can only get regulatory approval once it's been proven that it will be safe. Again, there's a bunch of things there, but only after all of this can a mine be built and operated. So just write these 2 parts here. So how do you actually mine uranium? I went down into a uranium mine. It was pretty freaking sweet. So you use, generally speaking, robotics and operators. So remember, 1, this isn't very big. The deposits aren't very big. And 2, it's very high grade, so that means it's dangerous. And 3, there's water everywhere because that's how it's gotten there. So we have to deal with that. So the deposits are really high grades and can be dangerous if it's mishandled. And remember, there is water everywhere. So the operators who control them remotely. So we either have 1, underground mining, 2, solution mining, or 3, open pit mining, which no one really does anymore. So you either have option 1, underground mining, or 2, solution mining. And again, half a football field in length and height. So write that down. So this gives you a general idea here. You do want to write this down, but really talk about this solution mining here. So underground mining and solution mining. How do you get the material out? Well, You use a jet bore, which shoots a bunch of really high pressure water into a small cavity, right? So let's imagine here's our little hole. Here's the uranium. I'm going to dig out a little cavity. I'm going to spray my water in there, and I'm going to collect all that water and sort it out. Now I have a giant ass hole in the ground, right? So now I have to fill that in with cement. Remember, there's water though. How do I stop all this water all around me from flooding into my cave here? I freeze it. I use liquid nitrogen to freeze the entire ground around it. So these are some pictures I took here. Again, water's everywhere, right? Here is those slurry machines. Remember, this spits out that high concentration of water and another hole over here collects it. So you want to write this stuff down. Wait, don't worry about that. But yes, you want to write the top part down. Check. So this is underground mining, okay? This is underground mining. We use water, but it's not solution mining. Solution mining is this thing here. With solution mining, you do not go underground. You stay on the surface. You dissolve the uranium. So you pump liquid underground, you dissolve the uranium, and you suck it back up, right? So here's my stuff, here's my ground, here's my uranium, right? So I'm gonna drill a hole in here. I'm gonna put some, I'm gonna say water, but it's actually solution. There's some chemistry involved. So it all dissolves, and then I suck it back up and I filter. It's as simple as that. That's what solution mining is. Um, hmm. So yes, you want to write this stuff down here. So in underground mining, I know it's kind of all over the place here. We have to freeze that water to prevent water inflows. Water and mines is bad. That's what kills people. That's what causes collapses. So we use liquid nitrogen to freeze it. This is just how nutrient mines work with their potash. They also then will concrete and bolt the entire surface of it. Look at this. They've they've put metal mesh on it to make sure nothing falls and hits someone on the head. They've bolted it. These bolts are like 6 feet long. They're huge. So we really make sure that everything is safe and cemented in place. So MacArthur River mines the ore out. Cigar Lake uses a jet bore. Okay, so you want to write all this. You want to write this down. You can watch this video here. I actually met this guy. You'll watch this video here. And another one. Cool. You can write this down, but we already talked about it. Yeah, you'll want to do this one here. All right, so this here, again, is a solution mine. So this here is a solution mine, right? Notice how no people are going underground, right? So they bring the solution in, they dissolve it, they suck it back up. Then they process it into the plant. We don't need to talk about open pit. That's fine. That's fine. That's fine. Radiation protection. So we're dealing with uranium. Obviously, that means there's radiation. Um, so starting out here, you're only allowed a certain amount of radiation in a given day. So safety is obviously very, very important. If you're exposed to uranium, high enough levels of it, that's bad. So we need to take precautions. We need to use PPE. We need to make sure there's good ventilation. We need to keep you physically away from the stuff. We need to give you shielding. For example, there might be, in some cases, a 3-inch block of iron or lead. In some cases, that might just mean kind of like a mud flat wall, basically, and that's fine. And also, we limit your time exposed to it. So these are all things. So you want to write that all down. Remember, you don't need to write this down, but everyone is exposed to it daily. Your biggest risk is probably radon gas. Again, you don't got to write this down. You do need to write this down, though. Every worker must carry a radiation monitor, and every day there's daily monitoring and there's regular testing of the workers. And these tags, which I will show you a picture of one in a second, is regularly tested. And if you are over your level, then one, they're going to figure out why that's the case, because if it's happening to you, it's happening to others. And two, that means that you're done work until we deem it safe enough for you. What that means is you might now have a paid month off work because you got a month's worth of radiation. So this here is a tag. You wear it on you at all times. And this is very regularly tested. So at this point, so we know that uranium is now a dissolved solution, right? So how do we process it? How do I separate the water from the uranium? Wow, I just talked for a half hour and I didn't even record it. So now I get to do it all over again. So imagine I have uranium. In this case, it's a juice crystal. I actually did this live on camera, but it didn't record. I pour that into my cup here. I have uranium. I pour a bunch of water into my cup as the water that's used to slurry it and turn it into a solution and extract it. How do I get the juice crystals back? How can you possibly get rid of water? A few ways. I can filter it, I can evaporate it, and I can boil it. Well, that's technically the same thing. So there's 5 steps here. You want to write all 5 steps of these down. One is leaching, right? So I put the uranium into water and it dissolves. Step 2 is I counter current decantation. So what that means is, here's a giant tank. Here's a big paddle that goes in it. This is all filled with water. The paddle spins the paddle spins one way, but the water spins the other. And so the paddle is going to catch the material and concentrate it. So it separates the solids, and then we filter it to remove the sand. So that's what these are. Again, you can see this, right? So the water's spinning one way, but the paddle in here is spinning the other way. So that concentrates all of the solids against the paddle in a simplified term. So now we need to extract the solvent. So this solution has uranium and other impurities, right? So I remove the solids, but I want the uranium. So I concentrate that and then I purify it using solvent extraction. Basically, they use chemistry at this point. Once it's concentrated, we extract it. Once I've extracted it, it's time for me to bake it. So I'm literally going to take this, convert this into yellow cake because it looks yellow by adding ammonia. This then gets spun around until it's solid and dry, and then it goes into a furnace. Once it's dried, then I package it. Now, each of these drums weighs 400 kilograms, which is about the weight of a small car. And these drums are then shipped to refineries to make the final product. Now, again, yellow cake, it's literally yellow. So these drums, this is a picture I took this summer, are heavy, 400 to 450 kilograms. Very, very heavy. This one here is like 440 kilograms, right? So that's over 900 pounds. Me for context. So what do I do with the waste though? So remember, step 3, what do I do with the impurities? And there'll be a little bit of uranium that gets in there. What do I do with the leftover solids? I add it to a tailings pond. So a tailings pond, it goes into a giant ass pond of water. As simple as that. And what happens to it? Eventually it sinks and it concentrates all at the bottom. So it's stored there. And then this gives me clean water at the top to send out and treat. So the bad stuff sinks and the good stuff floats. And I take what I need. So you want to write all of this down, but tailings ponds are used to consolidate and concentrate waste for long time storage. And there's a few reasons it's stored underwater. One, water is great for radiation protection. You can be 2 meters away from an exposed uranium rod underwater, and you will be perfectly safe. Um, but also it prevents just like, freezing it basically during the winter. It's tested pretty regularly, of course. Now, at this point, you were given there's a 5-page document for you that goes over this stuff. But basically, there's a 15-step process at this point from when I've received the ore to it's going all the way through the plant, yada yada yada, into the tailings pond. So that's this 15-step process, which you'll generally need to know. Cool. So what about reclamation? We've talked about this before with coal. With reclamation, once a deposit is exhausted or unprofitable, it's time to close the mine. So these mines need to have a reclamation plan that's approved by the government before being built. Write all this down. Reclamation returns to the site to a form that is safe and useful for nature and or people. And specifically, you want to try to make it similar or better than it was before. It's not always the case, but it often is. Sorry, my cat's eating plastic. So we reshape the land and we add vegetation, right? So this is the same picture here. Look at this lake. The same picture, it's the same angle. Look at what happened, right? So this is now useful for nature, right? There's clean water in ponds for animals and birds to come back and migrate back. There's lots of wildlife and forest and vegetation. It's useful. People can go there. So at this point, you're going to look into Cluff Lake. There's information provided for you in a different assignment below, but this is a beautiful case study for it. So why are they so strict on this? Why are they so strict on the reclamation process? Because Uranium City, which is about right here, was a bad case study. So that's where they abandoned it. They abandoned that region there. So they're very strict on it now. That is why they need to have the money for the reclamation plan established before they dig the plant. That money is set aside. So if the plant goes under, we can still pay for this reclamation process. So you'll look, you don't have to write this down because you're going to read into it. But again, look at this. These are the same photos. These are the same photos. These are the same photos. So watch this video. But generally speaking, there's a lot of careers and it's a growing field. So awesome.